Washington State is one of about 4 states in the US that generates more than half of its power from hydroelectric plants. And we kind of already know how those work. They're open systems, there's turbines involved, and while there are some interesting design considerations, the basics of it we sort of already know. Living in Washington, however, does not excuse you from knowing how power plants work in the other 46 states and really around the rest of the world. Most power plants look something like this, not necessarily located near water. Now you may look at this and immediately think that it's a nuclear plant, but actually, nuclear power, coal-burning plants, oil-burning plants, natural gas plants, all have characteristics that sort of make them look something like this. And so we're going to talk generally about how this sort of power plant operates, and then relate it to a thermodynamic cycle known as the Rankine cycle that we'll use to model these plants. So the first thing you need is a heat source. And again, that can be nuclear energy, you can burn natural gas, coal, whatever. That generates heat that goes into what I'm labeling the power station. The power station is actually the region where we're going to use the Rankine cycle. That's where a lot of the interesting thermodynamics happens, so we'll save that for later. If you're burning something like coal or natural gas, you may also want to add a smokestack to get rid of some, but hopefully not all of the combustion products. A nuclear plant will, generally speaking, not need a smokestack. Now, we also want to generate power. After all, that's the whole reason we built our power plant. So you have to have your power station doing some work on its environment through the transmission and generation of electrical power. Now, if you look at what's going on with the power station, that can't possibly be executing a cycle as drawn, right? Because we're attached to one thermal reservoir and we're getting work out, so we need to be attached to another thermal reservoir, and that one will be a cooling tower over here. And that's just designed to get rid of some of the heat that came from our heat source, went into the power station, but did not go into the generation of work. Okay. So generally speaking, nuclear, coal, oil, and natural gas power plants will look something like this. Now they may have more than one of some of these components, but the basic structures are there. So now we're going to focus on the thermodynamics of the power station. So let's gray everything else out, and we'll zoom in on the power station. Okay, I'm going to add in 4 components that are essential to any sort of power station like this: a turbine, a condenser, a pump, and a boiler. And some of these we've encountered in other contexts. Others, their function will become clear once we simultaneously plot out what's going on between states on a TS diagram. So let's start by just labeling state 1, which schematically I'll put between the boiler and turbine. Physically, they don't necessarily have to be arranged that way. And simultaneously, I'll plot state 1 over on the TS plot over there. So what we're going to do is pass through the turbine to get to state 2. So you can watch both on the schematic on the right and the TS plot. I encourage you to go back and rewind the video if you need to see it again. So let's go to state 2. All right. And as we go through the turbine, you can see on the TS plot, we moved vertically. So that means it was an isentropic process. That also tells us that there must not have been any heat transfer involved, right? Because heat transfer is area on a TS plot. You don't have area under a vertical line. Okay, so we did an isentropic process. It does have some work associated with it, though. And remember, the work ultimately from the turbine is the production of electricity going out to the environment. The value of W dot over M dot is just going to be the difference in specific enthalpies of state 1 and state 2. And it's been arranged so that that value is positive in this case, so we're doing work on our environment. Now, you may wonder what happened to all the kinetic and potential terms. Well, we're assuming that kinetic and potential effects are not important for the power plant. Even though I drew state 1 to be higher than state 2, that doesn't have to correspond to a physical change in elevation, certainly not an important one at least. Okay, so now we'll go through the condenser to get to state 3. So we do that, and we're going to go down through the condenser on the right. We're going from the right side to the left side of the TS diagram, so that tells us that indeed heat energy was transferred away from our system, which is consistent with the little wavy arrows under the condenser, right? You remember, area on a TS plot is heat exchange. So what is the value of the heat exchange? Well, under the assumption that we're not doing any work going through the condenser, and again ignoring kinetic and potential effects, Q dot over M dot is just going to be the difference in specific enthalpies between state 2 and state 3. So Q dot out over M dot is H2 minus H3. That's been arranged so that Q dot out over M dot is a positive number. So in the Rankine cycle, what often happens is that we arrange the variables so that all of the things on the left-hand side are positive. That way, if we take ratios or plug them into efficiencies, automatically we'll get sensible results. So that's all that's going on with the sign convention there. Okay, so now we've gone through the condenser. Now we're going to go through the pump. So in going from state 3 to state 4, we go through the pump, and there's just a little tiny transit over there on the TS plot. It is vertical. Maybe you can't see it's a pretty small line, but we went vertically upward on a TS plot. So in that case, remember, there's no heat transfer, but we had to have done work. It may seem strange, why would we do work if we don't want to change the elevation or anything like that with a pump? Well, the reason is to change the pressure. So what we're trying to do is actually move our water toward the boiler. When we do that, generally the water doesn't want to go to the boiler. There's a pressure difference, so you have to fight that pressure difference with a pump. So the work associated with the pump, again, it's just going to be a specific enthalpy difference, right? And if we want a positive number, it'll be H4 minus H3, okay? If you want your pump to operate, you probably also want to plug it in. So we'll want to take some energy, whether it comes directly from the turbine in our plant or whether we just have some external power source, doesn't really matter, but we'll have some work into the pump in order to power it. Okay, so now we've reached state 4, and you can see now we have to be a compressed liquid, right? Because we were a saturated liquid in state 3, we went vertically upward, that means that we now have to be a compressed liquid. Okay. The final step is to return to state 1, of course. After all, it's a cycle. But to do so, we're going to pass through the boiler, and this is where we accept heat from the environment. Specifically, we're accepting it from that heat source that, as I said before, consists of nuclear power or coal burning. Whatever is generating all that heat is going into the boiler to heat up our working fluid. So what happens is we go from state 4 to state 1, and on the TS plot, we follow an isobar. So we go up and to the right as a compressed liquid, hit the saturated liquid state on the left side of the vapor dome, cross the vapor dome horizontally, so we're at fixed temperature and pressure, until we hit state 1, which is back on the right side of the vapor dome. It's a saturated vapor. Okay, we've completed one Rankine cycle doing this. Now, the final detail of the boiler, the amount of heat that we accepted, Q dot in over M dot, is just, again, the difference in specific enthalpies. So the nice thing is, these cycles are simple in the sense that you're always taking the difference of specific enthalpies. You just need to make sure to pick the right values and to take the difference in an order such that the thing you get on the left-hand side is positive. Okay, so now what I'm going to do is tell you how any of this is useful, because we just computed 2 works and 2 heat transfers, but who cares, right? All right, so let's erase all of this stuff, and I'm going to arrange all of the W dots and Q dots that we computed over here on the left. So the sub T is for turbine, out and in are descriptive, they're telling you the direction of heat transfer, and then sub P on W dot is for the pump. So that's all of the stuff we had to do with this cycle. To compute the overall efficiency of this cycle, well, first off, we need to decide what kind of cycle it is. I'm going to wager a bet that it's a power plant, and so it's a power cycle. After all, if the pump requires more power than the turbine puts out, that's like the worst power plant ever, right? Okay, so it's a power cycle. That means we're interested in its efficiency, eta, and that's just the net work produced divided by the heat transfer in. So we'll write that as W dot T over M dot minus now the work required by the pump. So that does factor in the work that we have to take in to power the pump. And then we divide the numerator there by Q dot in over M dot. So that's just the heat transferred into our system. We can rewrite each of these 3 fractions in terms of the specific enthalpy differences, which we have right above. So let's rewrite in terms of the enthalpy differences. And we can simplify this a little bit to get that the efficiency is 1 minus the quantity H2 minus H3 divided by H1 minus H4. So the good news is, for a generic Rankine cycle, this is the formula for the efficiency. All you have to do for your problem is determine the values of H at states 1, 2, 3, and 4. The tough part, of course, is that generally speaking, power plants use water, and they're using a liquid-vapor mixture for most of the cycle. That means you're probably going to have to do things like use lookup tables or the NIST website to figure out the values of H. Those won't be as easy as they would have been for an ideal gas or a totally compressed liquid most of the time.